Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X researcher and professional physicist. And today I'd like to bring to you another one of my articles. This one's entitled Huge Gas Giant Planets in the Inner Solar System. Now, as I have shown in previous articles, Planet X system stellar cores which have come to the Sun turn into gas giant planets, which then orbit the Sun. And you may look at Article 523 entitled Planet X in the Solar System, Jupiter and All Gas Giants or Recent Acquisitions. While stellar cores which come to the Earth turn into Earth moons. And you may look at Article 526 entitled Planet X and the Moon has not always been in the sky for more details. Jupiter is about 1/10 the size of the Sun, and it ended up orbiting at a distance of 5.2 away from the Sun. Much larger stellar cores have come into the solar system and have been observed in the Sun's corona, which would have gone through the same re-energizing process that the stellar core that became Jupiter did. In other words, by absorbing electrons and matter from the Sun. And here you see 3 of these stellar cores. And this one turned out to be 7 times the size of the Sun. We're going to call it A. And this one, about the same size of the Sun, we'll call it B. And this one was about 4 times the size of the Sun, and we're going to call it C. Now, as gravitational energy increases in the direction of the Sun, so in the direction of the red arrow, the highest gravitational energy objects will end up orbiting closest to the Sun, and the largest stellar cores will end up with the most gravitational energy, and thus orbiting closer to the Sun than smaller stellar cores. So distance increases in this direction, but their size increases in the opposite direction. So that means that there should be an inverse relationship between size and orbital distance. But we do not know to what power. And in order to determine that, we are going to use the orbital parameters for the known gas giants. So here we have capital R stands for their radii, and that's in terms of the Sun's radius. Jupiter is 0.1, and Saturn, Uranus, and Neptune is 0.0837, and it decreases as we move down this column. And then their orbital distance is given by the little r. It's in this column, so it's 5.2 for Jupiter, 9 for Saturn, 19.2 for Uranus, and 30.1 for Neptune. So the relationship equation that we now have is capital R, which is their radius, is equal to R to the power of X. We don't know what X is. We have to find out what it is. So you take ln on both sides. That's natural logarithm on both sides. And that means we can then write the equation in this form. Ln R equals X ln little r. And now we can determine X from the slope of the graph we get by plotting ln R versus ln little r, which is shown below. I actually had to calculate what ln R and ln little r were. I just didn't want to put everything on that table. It gets a bit crowded there. But this is what we get when we plot these. And then we can, from the slope of the graph, determine what X is. That's determined from the slope of this straight line graph. It turns out it's minus 0.675, and which is extremely close to minus 2 over 3. Minus 2 over 3 is 0.6 recurring, or 0.67. So that means this is extremely close, and from real data this is very good. So we're going to take that to be the relationship, minus 2 over 3. That's the most likely real relationship. And the fact that the number is so close to 2 over 3, or 0.67, or minus, with the minus, but it's 0.2, is strong evidence that the observation-based theory, which led to the understanding that gas giants are re-energized stellar cores, and that smaller stellar cores would orbit further from the Sun, is correct. Now, so starting from the relationship we obtained by plotting the data, we have then that capital R is little r over to the power minus 2 over 3, which is equal to 1 over r to the 2 over 3. And that means we can solve for the little r. We just take this to the power of 3 over 2. R to the 3 over 2 is equal to 1 over r. And then the r becomes 1 over 3 to the power of 3 over 2, which is the same as 1.5. Now the stellar core, which is about the same size as the sun, would have a radius which is equal to the radius of the sun. And for Jupiter, we have radius of Jupiter is 0.1 times radius of the sun, and the orbital radius for Jupiter is 5.2 AU. Then if we use the equation we have, we can that equation here, then we write it for the stellar core, and we write it for Jupiter. We divide one by the other, and this is what we obtain. The orbital radius for stellar core B over the orbital radius of Jupiter is equal to r for Jupiter, the radius, Jupiter's radius, divided by the radius for the stellar core, all to the power 3 over 2. In other words, we can then calculate what RSCB is by just taking the this orbital distance for Jupiter to the other side of the equation, and then we put in the numbers. For capital R for Jupiter is 0.1 times r to the sun. R stellar core B is just 1 times r to the sun. And then, so we have 0.1 over 1 to the power 1.5 times 5.2. And we get 0.16 AU. So this stellar core would become a gas giant planet of about the same size of the sun, orbiting about between Mercury and the sun, as Mercury has an orbital radius of 0.39 AU. It's just a little over twice what 0.16 AU would give us. It would be 0.32. Okay, a little bit larger, but close. Then the stellar core C, which was 4 times larger than the sun, would end up at, and we're going to use the same equation, but now for stellar core C instead of stellar core B. And stellar core C has a radius which is 4 times the radius of the sun. So we have 0.1 over 4 there to the power 1.5 times 5.2 AU gives us 0.02 AU. And the stellar core A, which is 7 times larger than the sun, would end up at the same equation, except now we have 7 times radius of the sun here, and that would give us 0.0089 AU. So that's approximately 0.01 AU. Now let's see where these distances really are. The sun's diameter, which is twice the radius of the sun, is 0.01 AU. So this distance is the same as the sun's diameter. So this is Mercury's position at about 0.4 AU. So one of them would be about here. That's the stellar core A. No, that was B. So that was the one that was about the same size as the sun, would be about here. Then the other ones would be inside. The edge of the sun's outer corona is indicated here with this red line, and that's at 0.06 AU. So that means they would be inside there, inside the outer corona of the sun. But they are so large that that would mean that the sun would be inside the body of these objects. And since these objects are larger than the sun, they would have to actually go inside the sun in order to orbit at these close distances, which is not possible, since they will be repelled by the sun's core, which will thus push them outwards from the sun until their surfaces are some distance away from each other. So the closest distance, the stellar core A, and that was the largest one, 7 times the size of the sun, is at 0.04 AU. And we can see that from this diagram, because if the sun has radius r sun, this object has radius 7 times r sun. So the total distance between the center of the sun and the center of this object has to be 8 times r sun. And our sun is 0.005 AU. and 8 times that gives us 0.04 AU. So this distance, this minimum distance, is 0.04 AU. Then from that we can calculate the orbital period from Kepler's third law, which basically tells us that the period is proportional to r to the 3/2, or 1.5. So for the stellar core A with an orbital radius of 0.04 AU, and using the fact that the Earth's orbital radius is 1 AU and the Earth has an orbital period of 365 days, we can use this equation. We can use the ratio between the period for the stellar core and the Earth, and then we just have r stellar core A divided by r Earth. That's the Earth's orbital radius. So that would be 0.04 divided by 1 to the power of 3/2, or 1.5 times the Earth's orbital period, which is 365 days. And if we multiply that out, we get 2.9 days. So this gas giant, 7 times larger than the Sun, would orbit the Sun once every 3 days. Stellar core C, which is 4 times the size of the Sun, would not be able to get any closer than 0.025 AU by doing the same thing I did here to the Sun. And so its orbital radius would turn out to be 1.4 AU. 1.4 days. Then stellar core B, which is about the same size as the Sun, will become a gas giant orbiting the Sun with an orbital period of 23 days. So that's the one that was at a distance of 0.16 AU. So then stellar core A would have an orbital velocity, which is the circumference of its orbit, which is 2 pi times the radius of its orbit, divided by its period. And when we calculate that, we get 3.611 times 10 to the minus 3 times 10 to the power minus 3 AU per hour. Then we can calculate how long this object would eclipse the Sun as it passes in front of it once every 3 days. And we can deduce that from this diagram. So the Sun would become totally not visible once the stellar core, the right-hand side or its edge, would coincide with the Sun's right edge. And this is for an observer out here on the Earth. So until that edge got to that point, a part of the Sun would still be visible. When it got to that point, the Sun would not be visible at all. And then the Sun would not be visible until it started appearing after the object's left edge moved further than the Sun's left edge. And that would mean that the object would go through a distance of 6 times the Sun's diameter. And the Sun's diameter is 0.01 AU. So this distance is 0.06 AU. And then we can calculate how long it takes for the object to move through that distance, and it's 16.6 hours. So that would mean that the Sun would not be seen from Earth for nearly 17 hours every 3 days. This is if it was shining at all, as it does not seem to be, as it is never seen from Earth. And you may look at Article 500, the Sun is no longer shining review, for more details, and was already not being seen at all by 1998. And you may look at Article 536 entitled, Was the Sun Already Not Shining by 1998, for more details. The question then is, with such large gas giants orbiting the Sun, how are the STO images, stereo images, SOHO images even possible? Most likely the images we are being shown are very old images, and if there were large gas giants already orbiting the Sun at the time that these images were being captured, most likely something was done to hide the fact that the Sun was being eclipsed. Either way, some heavy doctoring has most likely being done to these images. So in conclusion, there must now be quite a few very large gas giant planets orbiting the sun, which would be eclipsing the sun on a regular basis, even if the sun was still shining. And these are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.